If you want to make a deck of cards truly random, the math is surprisingly specific. Riffle shuffle it 7 times, and every arrangement is about equally likely. But if you use an overhand shuffle, you'll be there a while. It takes over 2,000 shuffles to reach that same level of randomness. For 2 centuries, probability relied on a rule called the law of large numbers. It shows that if you run enough independent trials, like flipping a coin, the average outcome eventually settles and approaches a 50-50 split. But there was a problem with relying on this rule for everything. In the real world, events are rarely independent. They are almost always influenced by what happened right before them. In 1905, Russia was divided by revolution. This social tension reached all the way into the world of mathematics. Pavel Nekrasov, a deeply religious mathematician, pointed to statistics like birth and marriage rates to argue that because these numbers followed the law of large numbers, the human decisions behind them must be independent acts of free will. This claim was met with fierce opposition from Andrei Markov. Markov was an atheist who had no patience for using math to explain religion. He set out to prove that probability didn't require independence at all, and that Nekrasov's proof of free will was mathematically meaningless. Markov turned to the text of the poem Eugene Onegin. He counted 20,000 letters, tracking how often a vowel was followed by another vowel versus a consonant. He found that the letters were clearly dependent. The probability of the next character changed based on the one currently on the page. He modeled this as a chain. In this system, vowels and consonants are states, and the arrows between them represent transition probabilities. His data showed a 13% chance of a vowel leading to another vowel. When running this predictive machine, the ratio fluctuates wildly at first. Over time, it eventually converges to the exact 43% split Markov counted by hand. By proving that a chain of dependent events could still follow the law of large numbers, Markov shattered his rival's argument. He demonstrated that probability could be calculated without assuming independence, creating a new way to model systems where one step influences the next. This math eventually moved from poetry to the physical world during the Manhattan Project. Scientists needed to know exactly how much uranium was required to sustain a nuclear chain reaction, but calculating the behavior of trillions of neutrons was analytically impossible. While recovering from a brain illness, mathematician Stanislaw Ulam spent his time playing solitaire. He noticed that instead of trying to calculate every possible card arrangement, he could get a reliable statistical approximation just by playing hundreds of games and counting the results. When Ulam shared this idea with John von Neumann, they realized that neutrons were not like independent card games. A neutron's behavior depends entirely on its previous velocity and position. To simulate this, they would need a Markov chain. They defined the neutron as the state and mapped its potential paths. It could scatter off an atom, be absorbed and exit the chain, or trigger a fission event that released even more neutrons to start their own chains. They ran these chains repeatedly on the ENIAC computer to find the average multiplication factor. This method of random sampling to approximate complex results became known as the Monte Carlo method. Without these dependent probability chains, the team wouldn't have had the statistical tools to predict exactly when a mass of uranium would become a bomb. By the mid-1990s, the internet was expanding so quickly that search engines like Yahoo were struggling to stay relevant. They ranked pages based on how often a keyword appeared, a system that was easily manipulated by repeating words in hidden text. Larry Page and Sergey Brin approached the problem differently. They saw the web as a network where every link from one page to another was a vote of quality. They modeled the entire web as a massive Markov chain. In this setup, web pages are the states, and the links between them are the transition probabilities. By simulating a random surfer moving between these pages, they could track the percentage of time the user spends on each page. The more time spent on a page, the higher its importance and rank. To keep the simulation from getting stuck in dead-end loops, they added a damping factor. Most of the time, the surfer follows a link, but 15% of the time, they jump to a completely random page. This application of Markov's work became PageRank. It didn't just improve search, it built the foundation for Google's $2 trillion empire. In the 1940s, Claude Shannon expanded on Markov's original letter-counting experiment. But instead of predicting the next letter, Shannon used entire words as his states. He found that by looking at strings of previous words, he could generate increasingly coherent sentences. This became the basis for modern predictive text, which guesses your next word by calculating the probability of the sequence. Today's large language models use a more complex mechanism called attention to understand context, but the underlying act of predicting the next digital token is a direct evolution of the chains Markov built a century ago. Across all these fields, Markov chains function because of what's called the memoryless property. This property allows us to simplify complex systems by assuming that you only need to know the current state to predict what happens next. You can effectively ignore the entire history of the system. This model does have limits. It fails in systems with positive feedback loops, like global warming, where rising temperatures increase water vapor, which then traps even more heat and accelerates the process. But in systems where the next outcome is dictated by the step immediately preceding it, this simplification makes the impossible manageable. It is the reason we can shuffle cards, simulate atoms, and index the internet. A petty argument over poetry in 1905 provided the mathematical P to the modern world.